Hello, 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 OChem 1. I am so excited. Let's oxidize. All right, this video, we are going to take our alkenes and we are going to oxidize. All right, now this isn't the normal redox you've done in your Gen Chem classes. This is our organic version. We're going to focus on two reactions. We're just going to start with two different oxidations, by far the most common. The first one will be with ozone. So I actually included several links for ozone if you're curious and you want to look into ozone a little bit more than what we do in this video. And then ozone is really fascinating because it is really emerging as an awesome treatment in water treatment facilities used to clean up wastewater, especially with all the pharmaceuticals that are ending up in our wastewater stream. A normal ionic bond filter doesn't do anything to those pharmaceuticals, but ozone will. And you'll see in our process today that ozone will get right in the middle of an alkene. It's wonderful. And then our second most common is our potassium permanganate. Now this is something you saw in Gen Chem 2. If you remember your purple titration, that was KMNO4. And I'm including a bunch of links for those two. Both of these reagents have been around forever. Ozone, in fact, was discovered in the 1700s. Can you believe it? So both have a prolific career in organic chemistry. Excuse me. And so I just wanted to give you a million links for both of those if you're curious. They both do a lot of stuff. I want to start with just reactions of alkenes. But before we do that, we actually have to define what oxidation and reduction means for organic chemistry. It's not just your flow and counting of electrons like we saw in our Gen Chem. It's not quite the same, although both reactions will have a flow of electrons. KMNO4, you learned in Gen Chem 2 how that's a powerful oxidant. But I want to start by defining the very just basic way we're going to look at redox or oxidation and reduction reactions for organic chemistry. And it's a little bit more about levels than actual counting your oxidation numbers in your elements. And for organic chemistry, you know, everything comes back to carbon, and then everything comes back to our most basic carbon unit. If we then follow all single bonds and have hydrogen as what we're bonded to, our most basic unit for organic chemistry is methane. That's where we're going to start our definition. And as we swap out one of those bonds for something higher than hydrogen, which you know in theory is everything on the periodic table, back in the day, you would run a reaction with some source of oxygen, like light it on fire. And if you added mass or you added oxygen, you just did an oxidation. So for our oxidations today, both of our reagents, we're going to, in 1980s, air quotes, add oxygen. So if we take one of those bonds and we swap it out for an oxygen, and now we've just made methanol, the reagent we would need to do that is an oxidation. And we would consider that our methanol is a higher oxidation level than our methane. All right, so then let's go up even higher. Let's this time swap two of those bonds for oxygen, or again, something higher than hydrogen. And what would we end up with? Well, now we're looking at formaldehyde. So you'll notice that we're changing our functional groups. We went from an alkane to an alcohol to an aldehyde. Now, aldehydes and ketones are the same oxidation level. And we just did an oxidation to get there. And we can keep going. So what happens now if we swap 3 bonds with oxygen? What functional group do we get to that has 3 bonds to oxygen? That is the carboxylic acid. So that is our next highest level in oxidation levels. And then as we go one level higher, and I kind of ran out of space, but is it possible to swap all 4 bonds to hydrogen with oxygen? We sure can. And what we're going to make is carbon dioxide. So carbon dioxide is actually our highest level of oxidation for our methane or our carbon-containing compounds. That's the highest level. And in order to get to any of these levels, you have to do an oxidation. So if you're going to go from an aldehyde to a carboxylic acid, you have to literally do an oxidation. You can't just do an elimination reaction, or you can't just add water or something. You specifically have to do an oxidation. And then what's awesome is that this works in reverse. So our next video will be reductions, the other one. We're going to take the exact same definition, and now this time, if you wanted to go from a carboxylic acid to an aldehyde or ketone, what are you adding? Or even CO2 to a carboxylic acid. In each one of these levels, what you're doing this time is you're adding a bond to hydrogen. So for each level, you're going through and adding a hydrogen. This is our definition of a reduction. So anytime you take one of those bonds that's bonded to an oxygen or anything higher than hydrogen, and you replace it with a hydrogen, you are going to your lowest ranking, and your lowest ranking on the periodic table, hydrogen, you're going backwards and you're doing a reduction. So this is really how we're going to view oxidations and reductions. So in this video, let's tackle the oxidation part. And then in our next video, we're going to tackle the reduction part. And you can guess that in our oxidations, our reagents are going to literally add bonds to oxygen. And in our reductions, we're going to literally add bonds to hydrogen. So, and we're going to keep in mind those levels. Again, you can't go from an aldehyde or a ketone to an alcohol without actually doing a reduction. You can't just do wouldn't it be awesome if you could just do an elimination reaction to go from here to here, but you just can't. You have to do an oxidation. All right, so let's tackle our first example. Let's take a look at ozone. So I'm going to get all Gen Chem 1 on you and actually draw the structure of ozone. You maybe haven't seen ozone in a little while, but I guarantee you drew it in Gen Chem 1. It's one of the classic examples of formal charges on oxygen. And if you want to think about it, you could think about it this way. This oxygen is sharing just a little bit more than normal. This oxygen is sharing just a little bit less than normal. And then this oxygen is following those octet rules. So our ozone, even, you can listen now in the news and in advertisements. I've actually heard it where, well, if we breathe in oxygen, O2, O3 must be more better because, I know, not an English class, right? Must be mostest bestest because, oh shoot, now you get more oxygens. So there is lots out there for these ozone treatments and, oh yeah, we'll clean your blood with ozone. It's perfect. Well, no, what those formal charges mean is that, holy cow, this is reactive. So it is not the same as oxygen, but better because there's 3. In fact, you do actually make ozone from O2, and what you need is electricity to do it. So there are instruments called an ozonator. It'll take the air or oxygen from an oxygen tank. It'll pass a current through it and it'll generate ozone. They're actually quite common. I have used them. And then we're going to use in our reaction mixture, I'm going to keep it classic and modern. So we're going to use dimethyl sulfide. Let's draw that. But there's a huge variation here with how you work up your ozone reaction. You can add all kinds of things to ozone reactions and get different products. I'm going to keep it classic O3 ozone and DMS for the workup, and I'm going to show you what your products are, and then we're going to track those oxygens. But I'm not going to show a full mechanism because honestly the mechanism depends on the solvent, and it depends on what you have here to help the rearrangement that's going to happen. So I'm going to show you the first step, and I'm going to show you the intermediates, but the process of how that reaction happens is actually variable depending on your conditions. So I'm actually not going to ask you this mechanism anywhere on the exam. I will ask you to apply ozone. So this for us will show up in our synthesis questions, not in our mechanism questions. So anytime I don't give you the full mechanism, I then don't ask you the full mechanism. So why did I choose this one? This one's probably the most common. One of the most common solvents for this is methanol. That's because ozone is a gas, so you're going to bubble it through your reaction. And if your reaction is in methanol, your ozone will react with your alkene first, and then it will complex with your methanol second, and it will turn a very bright, vibrant blue. So you can actually tell immediately, shoot, go set up your reaction, sit there, a little ways away. Sit there, eat your lunch, watch your reaction, and when it turns blue, you know it's done. And then you blow air through it until the blue is gone, and now you know you've gotten rid of your ozone. And why would you care? If you've ever smelled that fresh smell after a thunderstorm, that's ozone. Awesome, right? Why wouldn't you want a bunch of it? Well, it's fatal above 9 parts per billion for you to inhale it. So you need to actually be pretty careful with your ozone. All right, so let's start to write what happens in this process. Again, I'm not going to draw the full mechanism. You can find parts of the mechanism online, and I've given those links, but I'm not going to ask the mechanism in this question. I do want to show you, though, how ozone starts that reaction, because we just had this video. We just did the video for our pericyclic reactions, and guess what? This first step of ozone is a pericyclic reaction. We are going to react in a ring. You've got this nice negative on oxygen, formal charge, and we are going to form a ring in that first step. How fun. So let's track what just happened there. All right, our double bond has now just formed a bond. Oh, that's not a bond. That is a lone pair. We have just formed this. Look at all those oxygens, now all neutral. And our alkene is now bonded to the ozone molecule. We just lost our double bond there. And now this first intermediate is called a malozonide. Now, since ozone has been around forever, 1700s. These oxidations are actually quite old, but because ozone is dirt cheap and it's really easy to use, it's a really nice reaction if you're careful with it and you're in the proper ventilation. It's still used all the time in oxidations, and like I mentioned earlier, it's used in water treatment plants because you can bubble it through your solution, and once it reacts, you'll see that we've got somewhat harmless products that are coming out of it. So it's a really good reaction. So a lot of the mechanistic studies for ozone were people actually isolating these intermediates. So the rest of it is sort of arrow pushing and guessing at how you get to these intermediates. But the malozonide and this next one, which is called the ozonide, both have actually been isolated. So you can guess a lot on an ozone mechanism. And like I said, the ozone mechanism to get to these sometimes is different depending on your solvent or what you add into that. And then from these two, and this is called our ozonide. But you have to be careful in isolating these. Back in the 60s and 70s, people were going crazy trying to figure out the mechanism for ozone. They're trying to isolate these malozonides and ozonides, and they're actually quite explosive. So you would be trying to, take your reaction mixture and kind of put it on your rotovap and remove your solvents, and it would blow up. And on one hand, you'd feel like, okay, I just made something that's awesome. And on the other hand, oh, you just lost everything because it just blew up. So you got to be careful with these, but the malozonide and the ozonide, those have been isolated and I believe have been radio labeled even. And then what happens is I just want to point out right here, okay, grab your colored pencil. In the malozonide, this bond is still intact, but then it rearranges and what, sweet Jesus, that bond is not attached anymore. So with this process of ozone, you are literally cleaving this bond. We are about to chop our alkene right in half. And then let's track it. We have got three oxygens, and I have 3 different highlighter colors. So let's go ahead, and I can't promise which oxygen ends up where, but all 3 of them end up in different molecules. So that first one, let's take that little blue highlighter right here, and what happens here is you make that aldehyde. So this whole ozonide rearranges again, and this is that blue part. And then with our green over here, that's the second half. So if you have symmetry like we do in this one, you actually just made 2 equivalents of the same compound, but they're now separate. You literally sliced your compound in half. And then this is what I mean too with your mechanism. Whatever you're adding to help these rearrangements right here, oh, I need to highlight that pink. This is where that third oxygen ends up. It helps the rearrangement. So if you're seeing a mechanism that's just rearranging and doesn't actually include your workup in it, then you know that that's somebody's just guessing there. So that oxygen ends up on our sulfur, and what our other product is in our reaction is actually one of our solvents, DMSO. And that is where the third oxygen ends up. Okay, so this seems like a lot of information. Again, I'm not going to ask you the mechanism, so let me show you my shortcut. Here's what I do. I take my double bond, and literally wherever you have the double bond, you are going to slice in half and replace both of those double bonds with oxygens. So I just literally break that bond and draw little oxygens in there, and look at that. Those are my 2 products. Oh, that drawing looks terrible. Let's do that again. Let's color code those. So wherever you have a double bond, cut it in half and put oxygens in there. And then remember that third oxygen just ends up as one of your solvents. So anytime you see ozone, you're going to literally cut that bond in half and then replace with oxygen. So out of this whole process, you're going to make 2 of those. You literally cleave that bond. So what happens then if you have ozone in a ring? Oh my gosh, one of my favorites. So check this out. Let's try our trick. You're going to slice that double bond in half. I like to draw it funny at first. All right, all of this, let's include the hydrogen. Let's include that hydrogen. All of this is still connected. All I'm doing is replacing with oxygen. And then we can just draw it prettier. That is that. Okay. So even if everything else is connected, anytime you see a double bond, you slice it in half and put oxygens in there. Now, what's awesome is we will notice this semester, this is the only way we will have of making an aldehyde. Our next oxidation is a kick in the chops. It's a little bit stronger, so we're going to have the same kind of shortcut, but we're not going to stop at the aldehyde. We're going to make the carboxylic acid. So this is beautiful. Anytime in synthesis in OChem 1 you see an aldehyde, you just immediately think ozone. It's awesome. All right, so let's try our next oxidation then, our KMNO4. Notice I'm using the exact same substrate. That way we can compare. All right, KMNO4 can be in some sort of aqueous acid or base. And sometimes you can see KMNO4 stops at a diol if you're reading in textbooks, but that's crap. I mean, as soon as KMNO4 is such a strong oxidant, what they're not telling you is you've got to have that reaction pretty cold and you've got to be pretty careful with it. So I'm not even going to give us that reaction. I'm going to go straight. Whoa, what did I do, y'all? I got so excited about oxidations, I think I hit it with my palm. I'm going to go straight to the carboxylic acid. So watch this. We're going to use our trick again, but this time I'm going to include the hydrogens. Okay, so this is where I want to redraw our little oxidation table and just remind us of our functional groups. Aldehyde, ketone, okay, acid, and CO2. And then I'm going to draw underneath there 1 bond to oxygen, 2 bonds, 3 bonds, 4 bonds. All right, so now let's take our KMNO4. KMNO4 is a stronger oxidant than ozone. That's why we're learning both of them. It's a kick in the chops. It is strong enough to break this bond and replace with oxygen, but wait for it. It is strong enough to break a bond to hydrogen. It's not going to break a single bond to carbon, so we keep these, but it is going to break your double bonds and your bonds to hydrogen. Okay, holy crap, how do you draw that? Now you notice we are not drawing a mechanism because it is single electron transfers and it can be quite crazy, and frankly nobody really knows. They can guess, and I'm pretty sure there's a complex of metals there. It's all kinds of crazy. All right, so watch this. I'm going to replace both of those with oxygen, but I'm going to replace these with oxygen also. So then what kind of functional group is this? Let that help you draw it. I've got 3 bonds to oxygen. What functional group is that? That is a carboxylic acid. So if you have symmetry like we do, then we just made vinegar in a very fancy way, and we made 2 equivalents of it. Okay. So same trick, you just are up a level in oxidation state. So let's compare. If we had done it with ozone, we make the aldehyde. We do this with KMNO4, we made the carboxylic acid. All right, so then I know you're curious, so just shut the front door right now. Of course, we're gonna put it in a ring. Let's do the same thing, only this time let's add in our hydrogen, okay? Let's do the same thing in a ring. We're gonna cleave this bond and we're gonna cleave this bond, and we're gonna keep everything else. So let's draw it funny first. I like to draw it funny just to keep my crap together. All right, what do we swap in for oxygen? We swap right here, and right here. So what does that make? That makes a ketone right here and a carboxylic acid right there. So then how do we actually draw that? We draw it like that. All right, aren't these kind of fun? No mechanisms for ozone or KMNO4. Both are going to be in your homework and both will be used in synthesis. And here's the super secret. If you see a carboxylic acid, then absolutely you need KMNO4. If you see a aldehyde, you need ozone. Okay, I want to do one more example up here because I do want to show why we don't make an aldehyde. So let's just take a nice alkene like this and let's draw everything out, all of our hydrogens. Is it possible to reach the highest oxidation level with KMNO4? Absolutely. If you have an exo double bond or something that is terminal like this one, holy crap, that's a whole lot of bonds we're about to replace with oxygen. Let's try it. Okay, and this one just looks a little bit funny until you match it with your functional groups. Okay, this one's easy, right? That's going to be your carboxylic acid. Okay, but then what in the heck do you do with this? We don't have a functional group that looks like this, but we do have a functional group with 4 bonds to oxygen, and that is our carbon dioxide. So remember this trick here, that if you come up with that 4 bonds to oxygen is your CO2. So when you're new with these, what I would do is have this little table